Right now, as you are watching this, a tectonic plate roughly the size of the state of Washington is tearing itself into pieces about 70 miles off the coast of the United States and Canada. And for the first time in history, we have direct images of it happening. In September 2025, a team publishing in the journal Science Advances confirmed the presence of large active tears slicing through the Juan de Fuca plate, including one fault where the descending slab has dropped by roughly 5 kilometers. In June 2024, the same research program published the first regional scale map of the Cascadia megathrust across 900 kilometers of coastline and found that the fault everyone assumed was one continuous structure is divided into at least 4 separate segments. The lead author of that study stated plainly that the models currently used by public agencies were built on limited, low-quality data from the 1980s, and the fault beneath all of it has not produced a major earthquake since the 26th of January, 1700 326 years ago. This is not a headline invented for clicks. It is 2 peer-reviewed papers, 1 research vessel, and a genuine rewriting of what we thought was under the Pacific Northwest. So today we are going to break down exactly what the scientists found, what breaking apart actually means in geological terms, whether it makes a megaquake more likely or less likely, and what the honest hazard picture looks like for the 8 million people living on that coast. No guessing, no dramatizing. Just the facts, the science, and the real stakes. Drop a comment right now and tell me this. Do you live on the Cascadia coast, Vancouver Island, Washington, Oregon, Northern California? And have you ever actually walked your tsunami evacuation route? Not looked at the map, walked it. Tell me your town and tell me how long it took you. Thousands of you watching this are inside the inundation zone, and I want to know how many of you have timed it. If you want to be the first to know every time the science on this coast changes, subscribe right now. It is completely free. A thumbs up helps enormously. Let us go for 5,000 likes so the algorithm pushes this to the people who actually live there. Let us start with how anyone learns anything about a fault buried under 2 kilometers of water and several more of rock. In 2021, the research vessel Marcus G. Langseth, operated by the Lamont Doherty Earth Observatory at Columbia University, ran a 41-day cruise along the Cascadia margin. The project was called the Cascadia Seismic Imaging Experiment, KC-21, funded by the National Science Foundation and led by marine geophysicist Suzanne Carbot with Lamont colleague Anne Bessel. The technique is essentially an ultrasound of the Earth. The ship towed a bank of air guns that fire powerful pulses of sound down into the seafloor. Those pulses travel through sediment, through crust, and into the upper mantle. Every time they hit a boundary between materials of different density, a sediment layer, a fault surface, the top of a subducting plate, part of the energy reflects back up. Behind the ship, the team towed a streamer, 15 kilometers long, carrying around 1,200 hydrophone receivers, listening for those echoes. Feed enough of those echoes through the right processing, and you get a cross-sectional image of structures no human will ever see. It was the first time a regional survey had spanned nearly the entire subduction zone, roughly 900 kilometers from Vancouver Island to the California border. The first paper, published on June 7, 2024 in Science Advances, delivered the finding that changed the framework. The Cascadia megathrust the enormous fault surface where the Juan de Fuca plate slides beneath North America, is not one uniform sheet. Carbot's team identified at least 4 distinct segments, each with different geometry, different sediment being dragged underneath, and different roughness. The boundaries between them line up with buried faults running roughly perpendicular to the shore, and with the seaward edge of rigid continental rock that appears to be forcing the segmentation in the first place. And within that, one segment stood out. From southern Vancouver Island down through Washington, the plate interface is markedly flatter and smoother, and the 2 plates meet at a shallower angle, which means a much larger contact area. Let me explain why smooth and flat is the dangerous combination, because it is counterintuitive. A fault surface that is rough and bumpy tends to snag. Stress builds in patches, and those patches let go individually, producing moderate earthquakes that release energy in installments. A fault surface that is smooth and continuous can lock cleanly over an enormous area, accumulate strain across all of it, and then release the entire thing in one continuous rupture. Bigger contact area, bigger potential earthquake. From studies of subduction zones worldwide, those are precisely the conditions associated with the largest events on record. So the 2024 paper told us the geometry. The 2025 paper told us the plate itself is coming apart. Published in Science Advances in September 2025 and led by Brandon Schuck, now an assistant professor at Louisiana State University, who did the work as a postdoctoral fellow at Lamont Doherty. The second study focused on the northern end of Cascadia, offshore Vancouver Island, where the Juan de Fuca and the smaller Explorer plate descend beneath North America. Combining the CASIE-21 images with detailed earthquake catalogs, the team found that the downgoing plate is not simply bending into the mantle. It is fracturing. They mapped several large tiers cutting through the slab. Along one of them, the plate has dropped by about 5 kilometers on one side, a vertical offset inside a slab of solid oceanic lithosphere. Schuck described it directly. There is a very large fault actively breaking the subducting plate. In his words, it is not 100% torn off yet, but it is close. The earthquake record backs the imaging. Along a 75-kilometer stretch of that tear, some sections are still seismically active, while others have gone quiet. In the Nootka Fault Zone, the belt of deformation between the Explorer and Juan de Fuca plates, the profiles reveal a fault network about 20 kilometers wide, with fractures that cut through sediment, through crust, and down into the upper mantle. The Explorer tear looks more mature, a sharper vertical offset, a steeper slab, and earthquakes clustering into an almost vertical wall. The Juan de Fuca tear looks younger, with more scattered seismicity and a broader buckle in the slab. What the team is watching, they argue, is a subduction zone dying. And here is where I need to slow down, because this is exactly the point where most coverage of this story goes wrong. Subduction zones do not last forever. If they did, continents would keep colliding and stacking until the oceans were gone. Something has to end them. Schuck's framing was that starting a subduction zone is like pushing a train uphill, enormously difficult. But once it is moving, it races downhill and cannot be stopped, and ending it requires something dramatic. What the images show is not a single dramatic event, but a slow, sequential derailment. The plate rips piece by piece. Fragments break off, new microplates and new boundaries form. Then the remaining plate keeps subducting until the next tier develops. The time scale for that process is millions of years, not decades. The tiers mapped in this study will take millions more years to separate completely. Carbot noted that scientists have long known subduction can slow or stall. What was missing was a clear picture of the process actually in action. So the honest headline is not that the plate is about to snap and unleash something. It is that we are watching a plate boundary die in slow motion, and it explains things we could not previously explain, including the fossil microplates off Baja California, the shattered remnants of the once enormous Farallon plate, which geologists have long recognized as the wreckage of dead subduction zones without knowing the mechanism that produced them. Now let us do the comparison that decides how seriously to take the segmentation finding, because the world already ran this exact experiment and it got the answer badly wrong. Before March 2011, Japanese seismic hazard assessment for the Japan Trench treated the subduction zone off Tohoku as segmented. The prevailing expectation was that individual segments would rupture on their own, producing earthquakes in the magnitude 7.5 to 8 range. Those were the events in the historical record. Those were the events the defenses were built for. Seawalls along the Sanriku coast were engineered against a tsunami consistent with that expectation. On March 11, 2011, multiple segments ruptured together. The result was a magnitude 9.0, roughly 30 times more energy than a magnitude 8, and a tsunami that overtopped the seawalls. More than 15,000 people died. The lesson was not that segmentation is a myth. The segments were real. The lesson was that segment boundaries buffer ruptures until the day they do not, and a hazard model built on the assumption that they always hold is a model that fails in exactly the scenario it most needs to survive, which is precisely why the Cascadia researchers were careful with their own language. Harold Tobin, a geophysicist at the University of Washington, director of the Pacific Northwest Seismic Network and co-author on the 2024 study, said the work cannot establish that only single segments will rupture, or that the whole thing will definitely go at once. What it does, he said, is strengthen the evidence that segmented ruptures occur, and there is a specific reason not to relax. There is good evidence that the 1700 earthquake, on the last one, ruptured the full margin, segments and all. That earthquake is one of the best dated prehistoric events in the world, and it is worth understanding how we know. Along the Pacific Northwest coast, there are ghost forests, stands of dead western red cedar killed when the land abruptly dropped and salt water flooded their roots. Tree ring dating puts their death in the winter of 1699 to 1700. On the other side of the Pacific, Japanese village records document a destructive tsunami arriving with no local earthquake preceding it, an orphan tsunami, on the night of January 26, 1700. Working backwards from the crossing time of the wave, the source was Cascadia, at about 9 in the evening local time. Moment magnitude estimates run from 8.7 to 9.2, 326 years ago. Geological records of past Cascadia ruptures suggest an average interval on the order of 500 years, with substantial variability. Some intervals a few centuries, some much longer. So what does the modern scenario look like? In numbers rather than adjectives. The Oregon Department of Emergency Management estimates 5 to 7 minutes of shaking along the coastline for a magnitude 9 or greater event, decreasing in intensity inland, FEMA's region. 10 Cascadia plan covers 27 counties across the Pacific Coast, Puget Sound, and the Columbia River corridor, and assesses every seaport on the Pacific Coast as at risk of complete damage. 36% of Oregon's coastal county population and 42% of Washington's live inside the tsunami inundation zone. The tsunami is near source, 15 to 20 minutes from shaking to water on parts of the coast. FEMA's published estimate for a magnitude 9 event is on the order of 14,000 deaths across Oregon and Washington, with other agency scenarios running considerably higher. Oregon's Cascadia Rising exercise scenario projected roughly 4,000 casualties in the city of Seaside alone. And in 2025, Washington's Emergency Management Division ran its own casualty study using state census and building data after years of local emergency managers arguing that the federal modeling understated the risk. Pacific County's Emergency Management Director, Scott McDougall, was blunt about that dissatisfaction. The state study modeled a reasonable worst case, a magnitude 9 at 2 in the morning on a midsummer weekend when coastal populations peak. So when you see the phrase, a tectonic plate off the U.S. coast is breaking apart, the instinct is to assume this is new, accelerating, and pointing at a date. Is the Pacific Northwest in more danger this year than last year? The honest scientific answer is no, but the picture is more nuanced than a simple no. Nothing in either paper changes the overall hazard level at Cascadia. The researchers said so explicitly. The zone was already capable of producing very large earthquakes and tsunamis, and decades of paleoseismic work established that long before these cruises. Slab tiers are not exotic, they are documented at subduction zones around the world, and they operate on timescales that make a human lifetime irrelevant. The plate has been subducting at roughly 4 centimeters a year, about the rate your fingernails grow, for tens of millions of years, and it will keep going. What genuinely changed is the resolution of the picture. Public agencies were working from 1980s era data. They now have a segment map, a measured geometry, and a structural explanation for why the fault behaves the way it does. The open scientific question the team is now working on is whether a rupture can jump across one of these tiers, or whether the fractures act as barriers that stop it. Incorporating that into rupture simulations is what will actually sharpen the forecasts. And researchers indicated that assessments capable of influencing building codes could follow. What changed is not the plate. What changed is that we can finally see it, and that 8 million people now live where in 1700 there were coastal villages. Let us be direct about the practical message here, because information without action is just anxiety. Tohoku died with accurate science and an incomplete model. Cascadia's last rupture killed and displaced coastal communities that had no instruments and no warning, and left the evidence in tree rings and Japanese village ledgers. Today there is a segment map, a tier map, a tsunami inundation map for nearly every coastal town, and a state-level casualty study built specifically because someone thought the federal numbers were too optimistic. Here's what you can control, and most of it takes one afternoon. Find your tsunami inundation map. Oregon Dogami, the Washington Geological Survey, and County Emergency Management all publish them by address. Then walk the route on foot and time it. If it takes more than 15 minutes, that is information you need before the ground moves, not after. Learn the rule that replaces waiting for an official alert. On this coast, the shaking is the warning. If you are in the zone and the shaking is strong enough that you cannot stand, go to high ground immediately, on foot, without waiting for a siren or a phone. Roads and bridges may already be gone. Keep 2 weeks of supplies, not 3 days. The region's own resilience planning assumes coastal communities could be isolated for weeks. Secure your water heater and your tall furniture. Keep shoes and a torch under the bed. Agree 1 out-of-area family contact. And if you are inland, understand that 4 to 6 minutes of shaking damages inland infrastructure too. The tsunami is a coastal hazard, but the earthquake is a regional one. Final thought. The Juan de Fuca plate is one of the last surviving fragments of the Farallon plate, a vast slab that once carried an entire ocean floor beneath North America. Almost all of it is gone, consumed, its remnants scattered as microplates and fossil fragments along the western margin of the continent. What is left offshore is now tearing apart along its own fault lines on its way to joining them. We cannot stop that. We cannot predict the day the locked segment finally releases. But for the first time, we can see the machine, in resolution, from a ship towing a 15-kilometer ear across 900 kilometers of ocean. 1700 showed what a full margin rupture at Cascadia looks like when nobody is measuring. Tohoku showed what happens when a modern society measures carefully and then trusts a model that assumed the segments would hold. The Pacific Northwest now has better data than either of them had, and the only question that matters is whether it gets built into codes, plans, and evacuation routes before the fault stops waiting. The plate is not breaking apart on a human timescale, but the strain that has been accumulating since 1700 absolutely is. We will keep tracking every study and every model revision as it comes. Subscribe so you do not miss it. And leave that comment below. Have you actually walked your evacuation route, and how long did it take? Because these are not just geological events, they are human decisions.